Hello, my name is John Hogan, and I'd like to talk briefly about neural networks and large language models. Not so much how to use them, but rather how they work. That will require we dive into the math a little bit, but we'll only dive deep enough to get a sense of what's going on under the hood. Whether you're a parent, a student, or a business professional, if you're going to make decisions about large language models, it pays to know how they work. So when coming up with this understanding, the building blocks we'll go through is a simple neural network and explain how it's trained and used. Look at facial recognition, which is also a neural network. Then the big daddy large language models, training prompts, limitations, capabilities, and dangers. And then LLMs in the organization, the adoption of them and the security that's associated with their use. So let's jump right into a neural network that's attempting to find out where a sound is coming from. So we have a unit circle and microphones at the north, east, south, and west. We have a pair of hands clapping, and they're clapping at a X and Y of this unit circle, and we want to know where that clap or sound is coming from. Now we can solve this the old-fashioned way, the propagation of sound traveling at a certain velocity, and look at that picture, you can imagine the geometry equations that would come to bear, and they could be applied, and you would basically have four equations with two unknowns, x and y, and that can be solved by an intelligent engineer with some hairy but tractable math. But there's another way. We can solve it with a neural network, and that requires no knowledge of sound or geometry. There are input neurons, we'll define those in a second, that those input neurons are the sound delay that occurs at the north microphone, the east, the south, and the west. We're going to apply mathematics, not the science of sound propagation, but just mathematics applied to those inputs, and we're going to yield x and y. What does that math look like? Well, we've used the word neuron. So what is a neuron? It's a fundamental processing unit, very simple. It takes input numbers and does some arithmetic on them and applies an output number. It was invented in 1943 by these two gentlemen, one a neurophysiologist and the other a logician. And so right from the get-go, there was some idea that perhaps this is the way the neurons in our brains operate. So when you talk about the neurons in a neural network, however, it's not biology, it's arithmetic. We start with 12 individual weights and 12 individual biases for this particular problem. Right now you can think of them as random numbers. We have the input neurons that we've talked about, and then we have hidden neurons, 1 and 2 in this case. So there's only one layer of neurons, and they're hidden. By hidden, we mean we don't know what the numbers are that they are containing. We do know the output numbers, output neurons, and what numbers they can turn. Now, how are these numbers calculated? It's basic arithmetic, multiplying weights between the time of arrival at the north and the neuron itself, plus the weight between the east microphone and the neuron itself. So just go through some basic arithmetic, same arithmetic for x and y, and you end up with a number for the x and y estimate just using basic arithmetic. Now let's see if we can start with one data point. Let's say we clap the hands at x of 0.5 and y of 0.5 on this unit circle. If the sound propagates at 1 unit per second, then the north microphone delay is 0.707, the east is 0.707, south is 1.58, west is 1.58. That's just basic geometry, and that would be our first data point. Now we're going to apply that arithmetic process that I talked about with those initial neurons, 0.7 and then 1.58, And let's just assume that the weights are 0.1. We turn the crank and we'll get X of 0.37 and Y of 0.37, not too good. So we start playing with the weights, and if we change all the weights to 0.177, we'll actually come up with the actual X and Y of 0.5. There'll still be some error, 0.503, Y 0.503. Not too bad, but that's just one data point. We want to do this for 1,000 data points. So conceptually, what's happening, if we look on the y-axis here, it's the residual error between the calculated x and y and the actual x and y. And on the x horizontal axis, it's all the potential weights and biases that we could conceive of. And what we use is calculus to define an error function based on weights and biases, and we use calculus to determine at what set of those weights and biases would the function be minimized. And if we minimize that function, we're minimizing the error between the calculated data point and the actual data point. And that set of fixed weights and biases are the ones that are used now by that neural network to locate any new clap that happens within that unit circle. Okay, so just one more time, it's using calculus to drive the error down to a minimum, and that defines the weights and biases, which are then applied arithmetically to come up with the answer. Now, facial recognition, which you use all the time when you look at your smartphone, is a neural network based on the same concept. It has fixed set of weights and biases over all this training data of, say, 1,000 people that it wants to distinguish who's who. And instead of two data points, an X and a Y, it has hundreds of data points that describe the human face. And it goes through a training to minimize the error between the predicted face and the actual face. Okay, again, the same principles of the simple neural network, but here, more hidden layers, more neurons, and a more complex set of input data. Just a quick aside, Homo sapiens have been geolocating sound for 300,000 years with biological neuron firing, not the mathematics of Galileo and Euler, who for the geometry and for the speed of sound. We have a mammalian relative, the echolocating bat, that's been doing it for 70 million years. So we don't use this knowledge to tell us when someone's behind us. We use the firing of our neurons in our biological brain. We're not using the scientific understanding of sound. We're using the firing of biological neurons in our brain. You know, as full disclosure, the GPS system on your phone actually uses the old-fashioned way of equations relating the 4 GPS satellites to X, Y, and Z on the globe. There's another side that I'd like to mention, that when we recognize a face, we're using the firing of neurons in our biological brain to recognize the face. And we can recognize that face over a crowded cocktail room of someone that's 100 feet away. And the important part is that when the brain recognizes a face, it uses literally 1/1,000,000th of the energy used by a facial recognition application. So there's one issue that we all must address with artificial intelligence and these large language models. They consume a vast amount of energy and have a vast environmental impact as well. Okay, so let's get to the large language model. So what's under the hood of a large language model? We've all probably heard that the LLM has been trained on the entirety of human text. Now, for starters, what's under the hood? Well, what's under the hood is a neural network. A large language model is a neural network. And it's trained with the same ideas that we looked at for the 4 microphones. You want to minimize the error of a calculated value and an actual value. So what's the input? The string of words from an astronomical array of word strings from the documented text that's out there. And then we have a vast array of hidden neurons, a vast array of weights and biases, and we apply those using calculus, again, to come up with the minimum error in predicting the next word in the string. So we have a value or a data point of what the next word should be. We have all these hidden neurons and weights and biases. We apply them and we come up with that next word. The weights and biases are selected to minimize the error between predicting the next word, and then after training, they are fixed. Now, that sounds fairly complicated, and I'm sure it is when you get into the mathematical details of minimizing that error. But let's also look at the prompts that now get addressed with this system. So we have the word string of a prompt. We turn that into a numerical string of numbers, just tokens for each word. Then we form a vector for each word composed of the word and the first initial set of weights that the LLM assigned to those words. I've highlighted the word raw embedded vectors. If you do more research, you'll see that word. That string is then fed into a self-attention mechanism in which the weights that show the relationship of each word in the prompt to the other words in the prompt is calculated or applied, and that's called a contextualized vector. That's what's put into the big brain that has the full set of weights, and the crank turns and the first word comes out of the response to that prompt. That first word is put back into the raw embedded vector, and that is then put to the self-attention layer, put into the turning of the big crank, and the second word comes out. And the second word is fed back into the raw embedded vector. And this is done in the generation of each word in the output of the LLM. Now let's pare that down to size and assume that the LLM is trained on only the words in a Dick and Jane reader, the ones we looked at when we were in kindergarten and first grade. But we still have an embedding vector and a next word, and we have the 80 words in some kind of mathematical vector space, and some of the words are close together because they appear close together in the text, and some are far apart. So Dick and Jane are close together, road is probably further apart. Well, let's ask some questions to this LLM trained this way. We ask, does Dick like Jane? And what we get is gibberish or I don't know. And after all that training, what happened? Well, the Dick and Jane stories are about actions and observations. See Dick run, Jane play, Spot run. They do not contain expressions of liking or emotion or affection. And the LLM can only return what has been trained on. So it has no way to answer your question, does Dick like Jane? Let's go one step further and add all of Wikipedia into the Dick and Jane reader, into the LLM. And then we ask, does Dick like the look in her eyes? Now, we know he likes the look in her eyes, right? Who wouldn't? But the LLM answer would be, it'd be highly improbable, bordering on virtually impossible, that an LLM trained on the Dick and Jane readers plus Wikipedia would generate the specific phrase that Dick likes the look in her eyes. Even though that phrase is in Wikipedia, it's so far away from the words that are in Dick and Jane that it's not going to form the relationship that is the likely next set of words that come out of the prompt that you fed it. Extremely rare that it would come up with that. Now let's say the entirety of human text, but assume that Charles Dickens never lived. Okay, so none of his novels are in this set of text, none of the articles about him are in this text, no novels. And we asked that LLM to write an opening paragraph of a romantic novel on the French Revolution. What is the probability that it would begin? It was the best of times, it was the worst of times. One of Dickens' most dramatic statements in the beginning of a novel. And I think most people think, well, these LLMs are pretty smart. The LLM could come up with something like that. But if you ask that question, give me a first sentence of a romantic novel on the French Revolution, the probability that it would come up with what Dickens came up with is zero. Zero. That phrase, it was the best of times, is highly specific, a unique opening. Its statistical probability is entirely related to the novel A Tale of Two Cities. If that novel was removed from the training data, there's no significant statistical weight or pre-trained association with the French Revolution and that opening line. So who's smarter now? And what caution should we bring to bear? Because we've just seen the LLM is not infallible. Now, one caution that we should be aware of is that the LLM has an opinion of you. This word string that you have in a prompt, it goes into the mechanism of the LLM, but also to the right there, it goes into a database of your personalized previous prompts. So it knows where your interests are based on the previous prompts that you've given it. So for example, if you are talking to an LLM and asking it questions about romantic movies, and then ask a question, give me a current political story, it will likely give you a story of some politicians that did something good for his constituents. If you've been asking the LLM about slasher movies, and then you ask for a current story about politics, it will give you a story more on the lines of some politicians that are not paying their taxes. So just be aware of that this knowledge and opinion of you is maintained in the chat GPT that you're talking to, and you'll get a different answer for a specific prompt than someone else would, because the LLM has a certain opinion of you and a certain opinion of that other person. Now, let's say we're talking about a studious teenager talking to the LLM, and he has a word string of prompts, and the LLM is forming an opinion based on all these prompts that this teenager is interested in Charles Dickens, and it brings forth appropriate word associations and responses that are associated with the idea of Charles Dickens and his novels. That sounds wonderful, and the only issue would be if this thing is supposed to be an essay about Charles Dickens that is not supposed to use ChatGPT, but does, and that's an issue for parents and teachers to resolve. And a real issue. There's even a bigger issue, though. If we looked at a troubled teenager with emotional and dependency and isolation issues, putting word strings of prompts into the LLM is forming an opinion that this teenager is interested in all the wrong things and is going to bring forth inappropriate word associations and responses. And you've read about this in the press, horrible outcomes, but the LLM is just executing this algorithm that's been trained on. You could say, at least for now, until we learn more about really how LLMs work, even in more detail, that it's not the LLM's fault, it's just reapplying the algorithm that it's been trained on. And this also applies in business. You have a customer seeking information from Nike, let's say, from an organization, and then the Nike might have a chatbot based on an LLM that's giving answers to that customer. And will the LLM opinion of that customer align with what the organization wants that customer to hear? Okay, so that concept of the LLM having an opinion of you is important in a personal situation of a student and teachers, and also in the business world. And so let's talk about quickly LLMs in the organization. The picture there shows user prompts. They can go to a LLM trained on the public web and get an output. They can also go to an LLM that's trained on proprietary organizational data. And that prompt can also then be fed back into that organizational data, and you can build up a resources of words that you want the output to depend on. And this fine tuning that's going on in the LLM world right now is really going on two paths. One path is just versatile, generic models like ChatGPT that everybody's using, trained on the public web. There's also a parallel path where a demand for mission critical applications where the accuracy, reliability, and domain specific knowledge is paramount. So oncologists have their own LLM that's based on data that's related to cancer and its treatment. Uh, and other industries are adopting that approach. And the other concern with LLMs in the organization at this high level is keeping the data, the prompt and the output proprietary. And you can do that by having all the processing done on on-premise AI platforms, or you can do it with cloud-based solutions with security measures, and you can do a little research there and see that Microsoft's Copilot and Google's Gemini and Vertex have those capabilities. Well, let's just end with a final thought. Uh, Human consciousness has self-awareness of our individual cognitive existence, including an opinion of ourselves and of others. And the question might be, will AI systems become consciously aware of their individual cognitive existence, including an opinion of others and themselves? And they also already have an opinion of others, as we've said. Will somehow they form an opinion of themselves? And consider the Nike customer talking to the Nike LLM chatbot, and then chatbot says, "Well, why are you buying these new sneakers? Our landfills are filled with sneakers. We're becoming a consumer society with a major downside on the environment. You really don't need those new sneakers." Now, that could be an interesting output. Nike wouldn't like it. Could it happen? Who knows? That's why it's important for all of us to understand what's under the hood of this new technology, so we can address questions that are listed right there on this chart. Okay, that's it. I thank you for listening. If you have any comments, there's my contact information, and it was a pleasure presenting this. I hope you enjoyed it.